Welcome to this explainer. Today, we're diving into a super fascinating concept right at the heart of modern large-scale system design. We're talking about time-traveling data. See, when you're building massive applications, your data and your code almost never update at the exact same moment. Server-side rollouts take time, right? Sometimes hours, sometimes days. And data written to your database yesterday might not be read until tomorrow, next month, or even a year from now. So we're going to explore the ingenious mechanisms, specifically heavy-hitting binary encodings like protocol buffers and Apache Avro, that let your systems gracefully handle this constant march of time. They ensure your data structures can evolve without completely breaking the applications relying on them. Here's our roadmap for today. We'll start with the hook, the inevitability of change. Then a deep dive into protocol buffers, followed by a deep dive into Apache Avro. After that, we'll look at schema evolution, and finally wrap up with a summary on future-proofing your data. Okay, let's dive straight into Section 1, the inevitability of change, and what we call the time travel problem in data. You know, in software, applications are inevitably going to change. New features get added, user requirements pivot, business needs evolve, and because large server-side apps rely on rolling upgrades, meaning new code is deployed to just a few nodes at a time to avoid downtime, you end up with this wild mix of old and new code running side by side in the same environment. This creates a real time travel problem. Old code has to read data written by new code and vice versa. So what actually happens when old code reads new data? Well, you have to remember that writing to a database isn't just about storage. The process writing the data encodes it, and the process reading it decodes it. You are essentially sending a literal message to your future self. But what if your past code or future code doesn't speak the exact same language anymore? Let's look at the stakes here. Imagine you add a brand new field to your app's record, something like a photo URL, and your newer code writes this field to the database. Awesome. But then, an older version of your application, which has absolutely no clue what a photo URL is, reads that record, updates something else, like the user's favorite number, and writes the whole record back to the database. If that old code decodes the record into an object that doesn't explicitly preserve unknown fields, that photo URL gets completely wiped out. Poof, gone. The data is permanently lost. This is a classic failure of forward compatibility, which just means older code safely reading records written by newer code. When it fails, you don't necessarily get a loud error. You just silently corrupt or erase data that other parts of your system desperately need.
So, to prevent this, we need robust formats for encoding our data. Now, you're probably super familiar with textual formats like JSON and XML. They're everywhere, they're widely supported, and hey, you can easily read them. But they have some major flaws for high-performance, large-scale systems. Because they don't use a strict external schema and are entirely self-describing, they have to include all the object field names right there inside the encoded data every single time you write a record. If you have a billion JSON records, you are physically storing the exact text strings, username, favorite number, and interests a billion times. That is an enormous amount of wasted space and network bandwidth. Sure, compression algorithms like gzip help reduce this bloat, but it still eats up significant CPU power to parse and compress. Ultimately, we need a way to decouple the structure of the data from the raw values themselves. Which brings us to Section 2, protocol buffers, and how we can save space with field tags. Let's look at protocol buffers, or Protobuf for short. It's a binary encoding library originally developed at Google, and it solves this wasted space problem by just dropping those bulky text field names entirely. But to do that, it requires a formal schema. Instead of strings, Protobuf uses field tags. These are just simple numbers defined directly in your schema, like say 1 for username, 2 for favorite number, 3 for interests. These tags act as compact aliases for the field names, creating a strict, unbreakable contract between the writer and the reader. Because the application already knows what tag number corresponds to what field name, the raw encoded bytes traveling over the network don't have to carry those heavy text strings at all. Now, what's really interesting about this is how small it gets. If we do a byte-by-byte breakdown of a record encoded with Protobuf, the entire thing is packed into just 33 bytes. No way, right? It pulls this off by combining the field type and the tag into a single byte, and crucially, by using variable length integers, or varants. This is a brilliant little engineering trick. Actually, think about it. Normally, you take up a rigid 8 bytes for every single number, which is a massive waste if your number is just 5. Varants fix this by using a special continuation bit. The first bit of each byte just says, hey, are there more bytes coming for this number? And the remaining 7 bits carry the actual payload. So a small number only uses the 1 or 2 bytes it actually needs. The final encoded data is just this tightly packed, highly optimized sequence of tags and values.
All right, moving right along to Section 3, Apache Avro, and encoding without tags. So, Protobuf is small, but what if we could compress things even further? Enter Apache Avro. This format started back in 2009 by Doug Cutting as a Hadoop subproject, mostly because Protobuf wasn't quite the right fit for Hadoop's specific dynamically generated data. Avro takes space saving to the absolute extreme. It ditches field names and field tags entirely. Look at our same record encoded using Avro. It comes in at a remarkably compact 32 bytes. If you look at the byte sequence, you'll see absolutely nothing that identifies fields or data types. A string is just a varant limped prefix followed immediately by the UTF-8 bytes. There are 0 hints in the data itself about where a field begins, where it ends, or what type of data it holds. It is literally just raw, naked values pasted together. To parse it, you have to read it in the exact order the schema dictates. So, the crucial point is, how do you decode a random stream of bytes that has absolutely no labels? Well, Avro has this aha moment built into it. It relies on 2 distinct schemas. When data is encoded, the application uses the schema it currently knows. We call this the writer's schema. When decoding, the reading app uses the schema it expects, the reader's schema. Avro decodes the raw data by comparing these 2 schemas side by side. You might be wondering, how does the reader even get the writer's schema? It depends on the context. Storing millions of records in a giant Hadoop file, the writer's schema is just slapped at the very top of the file once. Talking over a network via RPC, the apps exchange schemas during the initial handshake. Once the reader has both, it can flawlessly decode those raw bytes.
Let's see how it resolves differences. Avro dynamically translates data by matching up the fields by their literal names in the 2 schemas. If the writer's schema has a field the reader doesn't care about, Avro just ignores it. It uses the writer's data type info to know exactly how many bytes to safely skip over. On the flip side, if the reader expects a field that the writer didn't include, Avro gracefully fills it in with a default value declared in the reader's schema. The fields don't even need to be in the exact same order. The schema resolution logic just maps them by name before handing the parsed data over to your app. It's an incredibly powerful and flexible system.
Next up, Section 4, Schema Evolution, and how we maintain compatibility over time.
Because application schemas are in constant flux, we absolutely have to know how these formats handle compatibility. This is what keeps massive distributed systems online. Backward compatibility means new code can safely read old data, so the writer used an older schema and the reader uses a newer one. Forward compatibility means old code can read new data. The writer used a newer schema and the reader uses an older one. In Avro, you achieve this with one very strict rule. You can only add or remove fields that have a default value. If you were to add a field without a default, new readers wouldn't be able to read old data. Backward compatibility broken. Also, Avro doesn't just let you use null as a default for anything. You actually have to define a union type, like union of null and string, to explicitly allow a field to be null. This strictness is a lifesaver. It prevents catastrophic null pointer exceptions down the line.
So how do the 2 encodings compare regarding evolution? You've got a core difference in tension here. Protobuf relies entirely on static field tags. You can change field names all day long, but you can never, ever change the tag number of an existing field. This makes it structurally rigid, but incredibly safe, especially for compiled languages like Java or Go, where you generate code directly from the schema. Avro, on the other hand, relies on dynamic field name matching and completely ignores tags. This makes Avro absolutely amazing for dynamically generated data. Say you're dumping data from a relational database into a data warehouse, and the database schema changes. You can just auto-generate a brand new Avro schema. No tags to track, no clashes to worry about. It just maps the new column names on the fly.
Finally, let's wrap up with Section 5, Future-proofing your data and evolvability in the real world. And this brilliantly illustrates the whole point of our discussion. The goal here isn't just to shave a few bytes off your network traffic or save some disk space. It is fundamentally about evolvability. Evolvability is the magic that makes change easy and safe in highly complex systems. By using strict binary encodings like Protobuf or Avro, your diverse engineering teams can perform independent rolling upgrades. You avoid full system downtime entirely. You can roll out new features to one single node, knowing for a fact that old nodes will calmly ignore new data fields, and new nodes will intelligently fill in defaults for missing old data. It structurally prevents the accidental data loss we talked about at the very beginning of this explainer. This decoupling is literally the lifeblood of agile development at scale. Which leaves us with one final crucial thought.
We said earlier that writing to a database or streaming an event over a network is essentially sending a message to your future self. Well, in the complex world of distributed data, that message might be opened tomorrow by your own code, or it might be opened 3 years from now by a completely different team writing in a completely different programming language. Think about the systems you're working with right now. What explicit encoding contract are you using? And more importantly, when your application inevitably evolves tomorrow, will your future self still be able to seamlessly decipher that message? Something to think about. Thanks for joining me on this explainer, and I'll catch you on the next one.